to deliver the topic on Euler tours and Hamiltonian cycles. Allow me to start my presentation by presenting the proponents of these two major concepts in graph theory, which are Leonard Euler and William Rowan Hamilton. To start with, Leonard Euler is a Swiss mathematician. He founded the studies of graph theory and topology. He held to be one of the greatest mathematicians in history and the greatest of the 18th century. He is credited for popularizing the pi symbol. Aside from this, he is also known for the concept of Euler tours and circuits, which will be discussed in this presentation. Next, we also have William Rowan Hamilton. He is an Irish mathematician and he made major contributions to optics, classical mechanics, and abstract algebra. He is known for the Hamiltonian mechanics. In this report, I will be giving him credits for making the concept of Hamiltonian cycles known in graph theory. This time, let us start with our puzzle time. In front of you are three diagrams. Which do you think of these can you draw without lifting your pencil, drawing each line only once? Can you start and end at the same point? Hold on to your answer and let's go back to this once I finish discussing the concept of Euler tours. To start with, we have Euler tours. Euler tours and circuits. Euler tour is a path through a graph that visits each edge exactly once. Euler circuit, on the other hand, is an Euler tour that starts and ends at the same vertex. These are actually, as I mentioned a while ago, are named after Leonard Euler, who cracked this problem and founded graph theory in 1736. Some observations for undirected graphs are an Euler circuit is only possible if the graph is connected and each vertex has even number of edges on the vertex. Second, an Euler tour is only possible if the graph is connected and either all vertices have even degree or exactly two have odd degree. The question is, why do you think these observations are true? Let's go back. Actually, the first observation about Euler circuit is only possible if the graph is connected and each vertex has even degree. It's because it needs one edge to get into vertex and one edge to get out. On the other hand, an Euler tour is only possible if the graph is connected and either all vertices have even degree or exactly two have odd degree. It's because we could start at one odd vertex and end at the other. So this is the main reason why these observations are being observed and being accepted. Next, Euler circuit problem. Given an indirected graph G, find an Euler circuit in G. So note, we can check if one exists in linear time. So how? We will know it later on. So given that an Euler circuit exists, how do we construct an Euler circuit for G? So this is the problem. Given a graph G, V with V and E as being the subgraph in it, find an Euler circuit in G. We can check if one exists if O of the absolute value of V time check degrees. So basic Euler circuit algorithm. Do a depth first search from a vertex until you are back at this vertex. Second, pick a vertex on this path with an unused edge and repeat 1. Third, splice all this path into an Euler circuit. Then, running time is equal to O of absolute value of V plus absolute value of E. Is the figure on the right familiar to you? Yes, because this figure is one of the figures that I have presented a while ago in the given puzzle. So hence, Euler circuit are given examples below given the original figure with the given one in the puzzle a while ago. So, given that B, A, C, G, D, E, F, we can have a circuit like B, C, G, D, E, and also a D, G, E. And that is why, for this certain figure, among the given three puzzles in here, only the first figure can be drawn without lifting your pencil, drawing each line only once. You can start and end at the same point. Let's now go and look for application of these Euler tools. We will be talking about Chinese Postman problems. Consider this situation. College open day. Chris is delivering leaflets to houses near the college. The leaflets tell residents about the college open day and apologizes for any inconvenience caused. Chris wants to deliver the leaflets as efficiently as possible. The question is, he is asking, what route can I take to avoid going along same street twice? This is an example of a Chinese postman problem. In this activity, you will learn how to solve such problems. So the map shows streets near the college. Think about, is it possible to deliver leaflets to the houses in these streets without traveling along the same street twice? So the college map is an example of a graph. Here are some others. A graph is made up of collection of vertices called nodes, joined by edges called arcs. A traversable graph is one that can be drawn without taking a pen from a paper and without retracing them the same edge. Think about it. Which of the graphs above can be traced without taking your pen from the paper? A Swiss mathematician, again, Leonard Euler, published the first paper on graph theory in 1736. The paper was based on the 7 bridges of Königsberg's problem. This was presented during our first meeting with Sir Paul Aceves. Residents of Königsberg wanted to know if it was possible to find a route which passed across each of the bridges only once. Euler found that order of the vertices determines whether or not a graph is traversable. If it is possible to traverse a graph starting and finishing at the same point, then the graph is an Eulerian trail. If it is possible to traverse a graph starting one point and finishing at a different point, then the graph has a semi-Eulerian trail. Let's talk about odd vertices. Odd vertices are the number of are actually vertices or graphs with one vertex or with one node, and you also have odd number of edges. So the left side are example of odd vertices and the right side are examples of even vertices. So for vertices A, it has order of 4. For vertices B, it has order of 4. C, order of 5. D, order of 2. E, order of 4. F, order of 4. And G, order of 3. So the only odd vertices are G and C. So an Eulerian trail is only possible if all vertices are even. Think about it. Can you explain why? A semi-Illyrian trail is possible with this given trail. This started at C but ended at G. The postman needs to return from G to C by the shortest route. Consider these distances. The shortest route is GE plus EC. The total distance traveled to deliver the leaflets is 1,691 meters. That is approximately 1.7 kilometers. The Chinese postman algorithm steps in solving this problem is, the first one is find all the odd vertices in the network. The second one is consider all the routes joining pairs of odd vertices Choose the routes with the shortest total distance. Step number 3, add in these edges again. This will give a network with only one vertices. Step 4, find an Eulerian trail. So just like as what we had a while ago, A has order 3, B 4, 3, 2, 5, 4, 3, and 2. So you can now find those vertices that has odd number of edges. Odd vertices are A, C, E, and G. And hence, possible pairings, AC plus EG is equal to 9 plus 8 is equal to 17 minutes. A plus AG plus AC is equal to 13 plus 7 is equal to 20 minutes. While AE plus CG is equal to 5 plus 11, which is 16 minutes. So by looking at it, so therefore if you are looking at the least number of minutes that we can travel, it's actually AE plus CG is equal to 5 plus 11 equals 16 minutes. The smallest total is the 16 minutes, as I've mentioned a while ago. Add these edges to the network. And the total time in the original network is 97 minutes. Shortest time, 97 plus 16 is 113 minutes or 1 hour and 53 minutes. Possible Eulerian trail is AB, DF, BE, AE, FG, HG, EC, GCA. And that's actually an Eulerian trail from the given problem. So this is an example of a Chinese Postman problem. So reflect on our work. First, an Eulerian trail is a path which starts and ends at the same vertex and includes every edge just once. Euler discovered that such a trail will exist if and only if all vertices are even. Now my challenge to you is, can you explain this? Why is this possible? The second one is, in network, the sum of the orders of the vertices is even. Same thing. I challenge you to explain this why. Lastly, in network, the number of odd vertices must be even. This time, let's go on and continue with Hamiltonian cycle. With Hamiltonian cycle, it's actually an Euler with a twist. It's known to be the Hamiltonian circuits. Euler circuit is a cycle that goes through each edge exactly once. Hamiltonian circuit is a cycle that goes through each vertex exactly once. So look at the difference. When we talk about Euler circuit, it talks about the edge. When we talk about Hamiltonian circuit, it talks about vertex. Does this graph have an Euler circuit? The one on the left? Alright. Does it have an Hamiltonian circuit? Does graph 2 has Euler circuit? And does graph 2 also have an Hamiltonian circuit? How do we find Hamiltonian circuits in graphs? So let's consider this problem. Find a Hamiltonian circuit in a graph of G given that V and E are actually subgraphs in it. So sub-problem, does G contain a Hamiltonian circuit? No. No known easy algorithm for checking this. So one solution is to search through all paths to find one that visits each vertex exactly once. Can use your favorite graphs search algorithm to find various paths. This is an exhaustive problem algorithm. So worst case, need to search all paths. So you really have to draw in this certain example. So these topics, I have included how to analyze exhaustive search for algorithm for the given problem. You can see this one. So this is actually from the original problem which is graph number 2. And I have included there all the trees possible. And it actually you will be resulting to exponential time. So search tree for path from B is the result of this given analysis. So how bad is exponential time? This is also included in my presentation, but then I won't be dealing much with this one because I will be dealing with only the Hamiltonian cycle. I also have included in my presentation the polynomial versus exponential time, and allow me to read the summary of um, this one. The P, the NP, and exponential time problem. All of these are currently known algorithms for NP complete problems run in exponential worst case time. So finding a polynomial time algorithms for any NPC problem would mean as the given figure on the right. So diagram depicts relationship between P, NP, and exponential problem or time, which is class of problems that probably require exponential time to solve. So it is believed that P is not equal to NP, and also it's not equal to exponential time problem. And this ends my presentation with Euler tours and Hamiltonian cycles. Thank you so much and have a wonderful day, everyone.